Hi guys, this video is going to cover ANCOVA, specifically between subjects ANCOVA and a two-way design. So what is ANCOVA? ANCOVA is this type of ANOVA that allows us to control for a variable. That's what the C stands for. So analysis of covariance that we know impacts the DV and the IV. So kind of in a Venn diagram format here, we know the IV impacts the DV, and we know the CV is also related. So this sort of allows us to control for a third variable problem, where we're not really interested in the CV so much as we're controlling for it to then look at what happens when the IV predicts the DV. So that normally would be considered error here, this section where the arrow is pointing. But since we're using that covariate, now we can account for it, and now it's less error in our design. And that's always a good thing when we have less error. So some abbreviations. CV stands for covariate, and sometimes you can think of it as control variable. So it's related to the dependent variable, and we're going to use it to adjust to the dependent variable to eliminate some sort of nuisance information or to control for something we know impacts the dependent variable. Those can be continuous, or they can be some sort of categorical variable, not just dichotomous, but any type of this or that variable. CDVs are used to adjust DVs so that we can hopefully create larger differences in our IV, but in reality just enough control that we know that the differences in the IV are not due to these other variables. Okay. If it's actually related to the dependent variable, it does help control for error variance. Our independent variable in this type of design, because this is an ANOVA design, should be some sort of categorical, so can be grouped or can be manipulated. Our dependent variable needs to be continuous, or we should switch and do some form of log regression. So this is the variable we're going to use to look at expected change between groups. So kind of the relationship of this to ANOVA is that it's ANOVA plus control, or covariance. ANOVA and regression are mathematically the same thing, so it's fair to kind of interpret ANCOVA as sort of a halfway step between the way that people analyze ANOVA and the way people analyze regression. So it's kind of like a regression, then an ANOVA. So first what we're going to do is control for the variance between the DV and the CV, and then adjust the DV to not include the CV, and that's a regression style control, and then do an ANOVA on those adjusted means. Okay. So in a between subjects design, we're still going to look at Levines for homogeneity. Our Posthoc test is going to be independent T, or between subjects ANCOVA on those adjusted means. And we can use a post-hoc correction of Tukey or an R. We're more than likely going to do Bonferroni. In a repeated measures design, we can get Mockley's for sphericity if we have more than 2 levels. Our post-hoc test can be dependent T or a repeated measures, ANCOVA, and our post-hoc correction can be Tukey or Bonferroni, kind of depending on which program you're using. Okay. In a mixed design, it just depends. You can get both Levines and Mockley's. And the post-hoc test is dependent on which IV you decide to split on. So let's look at this chart. If levels are greater than 2 and is significant, we could do, for a main effect between, we could do independent T with a Tukey correction. If levels are equal to 2, we can interpret those means. For a main effect of repeated measures, we would do dependent T. For the interaction, we would split on one of those IVs and then do some sort of correction based on the type of IV. Or do the test based on the type of IV. If that interaction is significant, people will often ignore any analysis on the main effects. And that's because adding more post-hoc tests does increase type 1 error. And you're interested in that interaction, so why are you only looking at the main effect anyway? So we're just going to make sure to follow up with the correct test type so that we don't mix and match between dependent and independent designs. Okay, so something new to this section over other ANOVA sections is that we need to find those adjusted means. So we're going to have to do something a little different to calculate effect sizes and post-hoc tests on adjusted means instead of just normal means, because otherwise you've wasted your time on ANCOVA. So we're not going to use pairwise t-test because that would calculate on the non-adjusted means. And so this is where Tukey is going to come in. Now we could do Bonferroni as well, but we're going to do Tukey. Because Tukey is actually a little less stringent than Bonferroni, but Bonferroni can be easier to run sometimes. Tukey, what it does is it corrects on the mean difference score that you need to find a significant difference instead of P. Now, that achieves the same effect. It's just that Tukey and Bonferroni work on different parts of the the analysis for correction. So Bonferroni works on p-values or cutoff scores related to those p-values. Tukey works on mean differences, but either way, the output in R shows you an adjusted p, so you can continue to use the big important rule and look for p less than 0.05 or any other alpha that you're interested in. So the assumptions are pretty much the same. So accuracy, missing data, outliers. Now we can use Mahalanobis instead of z-scores for between subjects designs because we're going to have now at least two columns, the DV and the CV. So we want to screen both of those. For additivity, if you only have one covariate, it's not necessary. If you have two or more covariates, you want to make sure that your covariates don't overlap too much. And this is going to be a special rule that actually maps onto a regression analysis where we don't want R to be greater than 0.7. Highly correlated CVs cause you to lose power because when two covariates are related at 0.7, that means they overlap in 50% of the variance. So you're almost wasting your time by using both of them. Linearity between the CV and the DV is kind of the point, so we'll want to make sure that those values are linear, and we're going to use our QQ plot like we've been doing. We want CV and DV to be normally distributed, and we're going to use our fake regression and look at a histogram of the residuals. Homogeneity and homoscedasticity, we're still going to use our residual scatter plot, but potentially we could also add Mauchly's and Levines. Remember, you do not want those to be significant. And for homoscedasticity, that residual plot's our only option. So we just don't want a megaphone shape of the relationship between the CV and the DV. Okay. So we're going to do a all between example and just have some little comments here and there about how one might apply this to repeated measures. And so this is an example from the Tabachnik and Fidel book, where we're looking at participants' attitudes towards the use of drugs. But controlling for their physical health symptoms, because people who report more symptoms likely have more positive attitudes because they're sick. And then we'll look at employment status and religion to analyze those group differences. So our IVs are employed versus not, religion, non-Jewish, Protestant, and Catholic. Our CV is physical health, where higher scores indicate more health problems. Attitudes towards drugs is our DV. So let's try a power analysis. So our test family is F. Our statistical test here is ANCOVA. And that's where we're going to look at fixed effects, beta effects, and interactions because we have all of those. So let's pick F here. Fixed effects, beta effects, and interactions. Actually, the first one. It's the only ANCOVA option you've got, so I'm going to go with that. Click determine and direct for partial eta squared. And in this particular example, we're going to use a small effect size. So 0.01. Calculate and transfer to main. Alpha we've been using as 0.05 all year. Power is 0.8 as industry standard. Now let's get into this new thing. So numerator DF. If this is for main effects, it's levels minus 1. If it's for the interaction, it's levels minus 1 times levels minus 1. Let's do that interaction. I have that worked out down here, but it's 2 employed versus not times 4 minus 1 for our 4 religion groups. And so our numerator DF is 3. Oh, wrong window. Our number of groups, this is based on the number of levels for main effect or the number of conditions for interaction. The number of conditions is 8, so that's 2 times 4. And our number of covariates, hopefully that one's obvious, there's only one. So I'm going to enter. It's going to tell me I need almost 1,100 participants, which is a little ridiculous. So this design might not be feasible if we didn't have access to a very large participant pool. That's a rather large sample size needed, but if we imagine that partial eta squared is larger, that would decrease. But here we've estimated it at very small, just to kind of see what one might need. All right, so let's work through this and flip back and forth in R. And this is going to assume a little bit that you've been watching a lot of these videos. And so I've got the data set loaded, and it has extra things in it. So let me just show you the names. So what are the columns that are in this data set? So we've got a subject number, attitude towards drugs, physical health, mental health, psychotropic drugs, employment, and religion. I'm just going to drop everything I don't need. So I'm going to keep 1 through 3 and 6 and 7. Because those are only the columns I'm going to use. So I'm going to look at my summary here. And my summary shows that I have a religion group that is blank. So I want to exclude those people because I don't want to use that. And it's going to treat that as a level, which we don't want to do because that'll decrease power. So I'm going to create a no typos data set. I'm going to look at my religion table just so I can see what's there. And I'm actually going to use this as a good time to factor that variable to make it not be capital caps instead, and that will help us drop the level that we don't want, which is like a blank level, or it's just got a space or something about the way it imported. Okay. The other thing you can do if you just want to see what those look like is use the levels command. The levels command will give you all the levels. So I can tell it's a weird space that's in my data set. Okay. So I'm going to use my factor command here. I'm going to do the name of the data set. The levels as they are named in the data set. Remember, this has to match what's in the data set or you'll wipe them out. And then the new labels I want to include. I'm going to look at that table one more time, and now I can tell that it has actually dropped the space levels. And if I look at the summary, now I can see that those have turned into NAs. Okay. And so what I want to do with that is I just can't, even though I have missing data, I really probably don't want to guess their religion, first of all. And second of all, given this is ANCOVA, I don't have 20 columns, so I can't really estimate them anyway. Oops, sorry, wrong button. Okay. So what we want to do is just exclude those people. They'll get excluded in a step for Mahalanobis anyway, so I'm just going to let R take care of that for me. Right. So let's look at outliers. We want to calculate our Mahalanobis scores, but only on the CV and DV column. So Mahalanobis is the function. I want to use the name of the data set, but only columns 2 and 3, and that's because I want to use attitude, drugs, and physical health. I don't want to calculate this on a categorical variable or it will go bunk. It does not like that. When you do this, make sure you use that name in all 3 places. Okay. So the name of the data set, the column means, and the covariance labels. Okay. Now that gives us our Mahalanobis scores, but remember we got to know what to do with them. So we're going to calculate a cutoff score based on the big important rule, so 0.001, we want people to be really wacky before we exclude them. And using the number of columns that were entered into the Mahalanobis. So this should only be 2. Okay, so I'm going to calculate that cutoff score and then print it out, especially if you're in my class, because I'm going to ask you for it. So it's 1382 with 2 degrees of freedom. The summary command will allow us to calculate the number of people who are outliers. And remember that people who are true are less than the cutoff score, which is what you want. And so those values are okay. And false are the people that are outliers. So we have 2 outliers. And I'm going to create myself a no-out data set that excludes those outliers. Okay. Go back over here, scroll through. So with repeated measures in an ANCOVA design, we do have to be concerned with additivity, and you want things to be correlated because that's kind of the point. For repeated measures designs, which we're not doing here, but in general, remember the rule is that they cannot be perfectly correlated. For CVs, we don't want them to be correlated over 0.7 because that would imply that they overlap nearly 50%. So you're wasting your time using both of them. In a design, you want the CV and the DV to be related, so don't run this correlation between the CV and the DV and then exclude the CV because it's related to the DV. That's the point of what we're doing. So in this particular analysis, I am going to skip additivity because I have one CV and between subjects designs, so it's not necessary. But here are some rules in case you are doing something different. Okay. The next thing we're going to do is set up for the rest of our assumptions. So we're going to run that fake regression that's covered in our data screening videos by setting up a random variable. Remember here the number 7 is just a lucky number. It is not any particular reason why it's 7. You can use anything greater than 2. We're going to run that fake regression using only using all of our columns now except maybe a subject number. Create standardized or studentized residuals, so this will help with interpretation when they're standardized. And create z-score fitted values to help us interpret the homogeneity and homoscedasticity residuals plot. All right, I'm going to walk through this in the R side, but be sure you follow along in the notes if you have not run a bunch of these at this point. So we're going to look at a histogram of the standardized residuals. And what we're really looking for is for the data to be centered over 0 and mostly between 2 and 2. Okay? And this chart's pretty good. Now, if you aren't sure, remember this is a random analysis, so you'll get a different picture than I will. Run it a couple times. Now, don't run it enough times until you get the answer you want. Run it a couple times and make sure the answer is consistent. So here I have seen most of my graphs have been centered over 0 and between 2 and 2. A little bit of straggle, a little bit of skew over here, but probably nothing too huge to worry about. Additionally, we have more than 30 people, so given the central limit theorem, our ANCOVA is robust to violations of normality. For linearity, we're going to use the QQ norm function. And what we want is most of the dots to be on the line between 2 and 2. We're starting to get a little bend here, but this is probably pretty close. So normally hammock shapes are not good, but this one's fairly close to the line. If I was feeling unsure, I could run this several more times to make sure that this is not a serious bend. And it's pretty okay. Homogeneity and homoscedasticity. Ooh, that's a fun one. Often this will happen because of your categorical variables, but let's try running that again. See if that happens every single time. Yeah, no. So if you aren't sure, like I said, a couple times to make sure that it's not that random combination of data. And this is something I do as well when I run real projects. All right, let's look at homogeneity. This is not good. It's from 2 to 2 on the bottom, centered around 0. That's fine, but up here on this vertical axis is where the issue lies. And I saw this every time I ran this, weird clumping or not. So it mostly runs from maybe close to 2 to 4. So the spread in the upper quadrant is larger than the spread in the lower quadrant. So I would say we have issues with homogeneity. And we'll be able to look at Levines Test here in a minute to tell if it's something we should worry about. For homoscedasticity, I would say this chart's pretty good. Maybe it's slightly less spread over here than over here. So the problem is there's kind of dots missing up here. But this plot is pretty okay because the spread is relatively consistent. Maybe some dots missing here. Okay. All right. We've been using Easy ANOVA for all of our ANOVA needs. However, Easy ANOVA does not handle ANCOVA very well. Hopefully it's updated, but I'm going to teach you another way to how to do it. We've done all this. Okay. So Levines tends to be oversensitive, but if you're wanting to look at real numbers, it's a good way to start. But because we're not using Easy ANOVA, we have to get Levines from the CAR library. Okay. And the way we do this is do Levine capital T test, DV column tilde IV times IV. Okay. Data equals data set. Center equals mean because we're using means as our model for ANCOVA. If you only have one between subjects factor, you would just leave off this portion here. If you have more, you just keep adding multiply IV, multiply IV. This is very similar to the way that regression code is written for the LM function, which will be some of the next videos coming up in the class. Okay. And so let's try that now. So I'm going to load my car library. So got Levines Test, attitude towards drugs is predicted by employment times religion. Okay. Data equals no out, center equals mean. What you'll notice here is that our covariant is not in the analysis. Okay. And so for our grouped variables, we would say that Levines Test was not significant, and so homogeneity, while the residual scatter plot's a little questionable, it seems to be met. All right, you can also do sporicity here, and my suggestion for sporicity is just run easy ANCOVA anyway, because there's no other real way to get it. All right, now if we're working with repeated measures, be sure you switch from wide to long format, and then there's just an explanation of how to do that. What we're gonna do is pop down here to between subjects, and so we're gonna save our output as output. And we haven't had to do this before, so now we're going to use the LM function and use dv is predicted by the little tilde. Do IV times IV, otherwise you will not get the interaction if you just do a plus CV. I'm not going to multiply the CV because I'm not interested in the interaction of the CV. I just want to control for the CV. And then do data equals data set. So let's try running that. Now you could just use the summary function, which we've used for a lot of different things this year. However, that'll give you the summary in regression format. So we're going to use summary.AOV to see this in a format that we're used to looking at if we've been doing ANCOVA this whole time. So it's going to look a little different than easy ANCOVA, but what we want here is to look at each line separately. So the degrees of freedom here is the degrees of freedom numerator. The degrees of freedom denominator is here under residuals. So 451 will be our second number for each of our DFs. Sum of squares, mean square, here's F, and then here's P. So we could write this as 1 and 451 equals 7.7. P is equal 0.006. Okay. And what we'll do is use that sum of squares line to calculate effect size. So we're going to look at the omnibus test for our CV, so that's just the number I have written out here. And there's no ADA. So Easy ANCOVA is a great package because it provides ADA for us. Now we have to do it on our own. So the way we're going to calculate partial ADA squared is sum of squares for that variable divided by, ooh, check out this typo, sum of squares for the residual plus sum of squares for that variable. Whew. That is incorrect otherwise. Okay, so this is partial ADA squared. And so we'll take sum of squares for the variable over sum of squares for residuals plus that variable. Okay. And so the numbers here are going to be just a touch wrong because we need to add the sum of squares for that variable to the denominator here. And that's my fault. Okay, so I took 10 as my sum of squares for the physical health. My sum of squares residual I got from here under residuals. And I just saved it because I'm going to use it a bunch of times. Now what we need to do here is do plus 10 on the bottom. And I'm going to use parentheses, otherwise it's going to assume that I want to do the division first because R knows, please excuse my dear Aunt Sally. So I'm just going to fix all of these right quick here, so that you have the notes are correct. Ooh, that was a weird space. All right, so for that first one, we're actually gonna get 0.02. Okay. And I'll go through and fix the notes here to include the same thing here. So this is partial ADA squared, so you would consider including a little p down here to indicate that it's partial ADA. Okay. But this is approximately the right the way I would write this up in APA style. And so what does a significant covariate even mean? So a significant CV, scrolled a little too far here, implies that the CV is related to the DV. Therefore, it's a significant adjuster of the DV. And so we'll need to figure out what does that mean so we can explain it. So we're just going to run a correlation to figure out the direction and magnitude of that relationship. Right, so I fixed the partial eta squared values so they're actually correct now, and so we're going to use those here in a minute. Then I'm going to run that correlation between attitude towards drugs and physical health, and it is 0.12. So a small effect which mirrors our partial eta squared of 0.02, so a small effect. That implies that as physical health goes up, meaning more health problems, attitudes towards drugs becomes more positive. Right? So now let's work on that ANCOVA, controlling for the relationship. So controlling for physical health symptoms, what is the relationship between employment and religion to attitudes towards drugs? So we get one F test for each IV. If you've watched some of our two-way design analyses, this should be familiar. Then we'll get one for the interaction. We'd interpret each separately, and we're just going to follow up that interaction if it's significant. All right, so for employment, and I got this from, let me come back up here. So 1, 451, F is 2.35, and P is non-significant. So employment overall does not have a significant effect on attitudes. Religion overall does not have a significant effect on attitudes. However, there's a small effect of attitudes given that interaction. Okay, so we'd have to decide if this was really important. But for the purposes of this learning video, we're going to walk through how one would analyze that interaction. Okay. So now we have to calculate the posthocs on those adjusted means. And that's where we run into trouble. So this is why we can't really use easy ANCOVA. Okay. So to get those adjusted means, we're going to load the effects library. The effects library will allow you to pull out those adjusted means, and the code is effect, IV column name, and then the saved output name. So it's called output here because that's what I saved it as. And I can do IV times IV to investigate the interaction. And so it's going to give me a little warning when I do employment only, because employment is not a higher order term, meaning it's just a lower order term. But here are my adjusted means for employment. I can get my adjusted means for religion. Now this is the name of the variable here from your data set. And then I can also get the adjusted means for that interaction. So here's what we would normally do with t-apply. Okay. So proof that these are slightly different. Right. So I got 7.71 adjusted and 7.68 non-adjusted. Okay. And there's not a big adjustment because the correlation between the CV and the DV was small. The larger the correlation between the CV and DV, obviously there's more to control for there, and so you're probably going to get a larger adjustment in the means. We still need standard deviation and N, and there's no other good way to do this than your normal t-apply procedure. Okay. Now the way that we're going to follow up is we've got to figure out, we have a 2x4 ANCOVA. Oh, cut and paste. Come on now. There's 8 boxes to consider. Okay. So I have to figure out if I want to go across or down because I want to find a variable to split and then analyze the others. So which way? Well, first, do what your advisor wants. That's my first rule always. The second rule is go with their hypotheses, so the way that you predicted to look at this. The third is, if those two are kind of like, it could be either, pick with a lesser number of tests, because a lesser number of tests is always good for type 1 error control. So we're going to split on the larger variable, religion here, so that we only have to run 4 tests. So if I split on religion, what that means is that I'm going to look at just none and calculate this pair, just Catholic and calculate this pair, Jewish, Protestant. So I'll have 4 post-hoc tests. If I split on employment, I would have a lot more because I'd have to do none to Catholic, none to Jewish, none to Protestant, Catholic to Jewish, Catholic, Protestant. There would be 12 tests total. 4 is a lot less than 12. So we're also going to do less work. All right, so I'm going to split on that. I'll go back to R in a second, but I created my table here where I'm going to do Catholic, employed to unemployed, Jewish, employed to unemployed, Protestant, employed to unemployed, none to employed to unemployed. So I just typed in those means, standard deviations, and in values that I got from effects and from tapply. Okay, so I've split the data set based on my religion variable. I'm going to use a new library called multcomp for multiple comparison procedures. Okay. So I talk about that a little bit down here. So what we want to do is basically look at like these little mini ANCOVAs. And so we're going to have to take out the variable we split on, or this is going to be very upset with you. So remember, when you split on a variable, you don't then analyze it. So be sure you always take out a split variable. Okay. The GLHT function will run on each output. So we're going to run 4 little mini ANCOVAs, and then we're going to use GLHT. ANCOVA output goes here. This linfect thing, which I just do not even remember what it stands for. It basically says, give me the output for the IV that I'm analyzing, and we're going to use Tukey. Okay. The IV name should not be in quotes in this particular section, and then we'll run a summary. So let's look at that practically. I'm going to skip the main effects thing here and come down to just the interaction. So I'm going to run a little mini ANCOVA. So look at what I did. I took the ANCOVA from before, scroll here. Took this ANCOVA from before and I just pulled out religion. So when I came down here for my Catholic output, it's the ANCOVA from before with no religion on the end. The data is for Catholics. And then I did that 4 times, once for each variable that I split on. Okay. Now I'm going to use that GLHT. I'm going to run that on my Catholic output. Leave all this goofiness alone. The data, the thing here now is you tell it which variable you want, because you have more than one here. I only want employment. So for employment, give me Tukey. Okay. Then we'll run a summary of that. The way the summary looks, if I can get this full screen here, is it shows me unemployed minus employed. So it's testing whether or not these are different from 0. It gives you an estimate of the difference in the means. It gives me a t-value, and then the probability of that t-value. So it's actually a nicer output than Bonferroni because it gives me the t-value. We're going to do that for Jewish participants, so that is also not significant. Protestant participants, which is in the marginal range, if you want to use those labels, or close, but not quite. I think the effect sizes are going to be more telling here. And last but not least, the none or other groups. So you'll notice that all of these are, in traditional terms, non-significant. And that will happen where you have post hoc tests, and this Word document here just kind of runs through all of that here, that none of the p-values are in the significant range, even though your interaction was significant. And I would say this happens generally when your interaction is close to 0.05, which ours was 0.04, and the effect size is small. So when you're looking for small effects and you start to break them down, you're going to lose power because the sample size gets smaller. And if all of the effects are small, why do we care? So this is where we're going to add the effect size to see if we should even care. But it's hard to find a significant result when the effects are small and we have lessened power because the sample size is decreased from the overall ANCOVA to these now smaller mini ANCOVAs. So this analysis, I'd probably be like, right, the effect is small. but showing you how this works. What I would do here is look at this p-value. And so if you want to use the term marginal, which I actually do not recommend, but this is sort of like traditional p-value interpretation, unemployed people, unemployed Catholics specifically, have a higher attitude towards drugs than employed Catholics. For Jewish participants, it's really not different. For Protestant participants, I guess if we want to call this marginal, we would say unemployed participants have higher ratings than employed. And this is where we're getting that interaction effect, is that actually flips for non-religious participants, where employed participants have a higher score than non-employed participants. And so the interaction is occurring because one of these is really not different. Two of them, unemployed is higher than employed, and the last one, employed, is higher than unemployed. So the interaction is because they flip. Okay. And then I explain here what will happen, why you might not get any significant post hocs. We've kind of already talked about this. And so you might reconsider the analysis you're running, and you might ask yourself, is this actually important? Okay. We're going to use that Moat library to calculate the effect sizes for this, and we're going to type these numbers in manually because we want to make sure to use the adjusted means. You can save those adjusted means if you know how to pull the numbers from a vector, but it could also be just as easy to look them up and type them in. So I relisted my means standard deviations, but if you've made this table that we've been working with, recreating, you've already typed these numbers out. So from here, I'm going to type all those in. I'm going to look at my effect sizes. And so when you run the Moat output, you want to make sure that you scroll up and look here at D for each one of these. So I've got 0.32, 0.15, 0.28, and 0.43. Okay. And blah, blah, blah. That's what I typed in here. So what does that imply? Well, it implies that the effects are small. So for this group, there's essentially no effect. For Catholics and Protestants and the nun people, the effects are small. And so it kind of depends on what effect size you believe is important. So if you think a small effect is important, then perfect, then go on and talk about the effect size, especially over p-values, as they're not totally the most useful things. And talk about how the effect sizes are different and one of them flips directions. If you don't think 0.3 is very important, you could say, even though this was significant, the effects show to be small. So this is really where the researcher makes their own decision. And if I were trying to publish a study, I would really want to report all of the numbers, so someone else reading it could decide for themselves whether or not they wanted to consider evidentiary value from P or from Cohen's D. Okay. Small rant there. So we're still going to use ggplot to make our plots. And this whole thing, shebang, walks through how to make a ggplot. Hopefully you've been kind of working through this either in my class or our series on these different design types. So I'm going to use my cleanup code just to make the graph not hideous, because the base ggplot options are not the prettiest. Okay. If you have NAs, you'll want to ditch them first. So let's look at a summary of no out. Oops. Right? And so we have some NAs in our religion category. Let's say that we don't omit them first. So I'm going to edit my own code here for a second to kind of show you. What's going to happen is it actually will create a separate category for our NA group here, which we don't want because we didn't actually analyze those people. So we're going to exclude them first. Okay. All right, so let's look here at our bar graph. Now without those NAs, whoop. And so the interaction happens because up, up, down, up. And so that's why we're getting a small but significant interaction. and also the size differences between Catholic and Protestant and none other and Jewish. So if I were talking about why I expected this interaction, I would talk about how Catholic and Protestant are larger than Jewish, and all three of those are in a different direction than none versus other, and really focus on those effect sizes. All right, but if you want to learn how to write one of these up, so you can check out the guide here, which walks you through how to include all these values. Remember, even though some of these effects are not significant, we would still include them. So don't not include an F value just because it's not significant. Be sure you include them. So I've got the effect of religion is not important. And then somewhere in here it says the effect of employment is not significant as well. So be sure you include all of them in your write-up, and potentially also a figure to help people really see that interaction. Okay. So this video has covered ANCOVA, starting with power, working through data screening, and going through the analysis.